Hi, welcome back. This is part 2 of our in-depth pathfinding video series, and in this video we're going to talk about how to implement our first search algorithm or pathfinding algorithm, which is the BreadthFirst Search. Okay, so in part 1 we built this simple structure where we could make our grid of walls that we will be able to walk around on, and we can click and draw walls wherever we want. Since the last video, I did add just a quick thing here where if you press the M key, it's just going to print out a list of all your walls. It looks like this. When I press M over here, it's just going to print a list of all those wall locations. And what that allows us to do is copy that printout and paste it right here and quickly make some walls. That way when I run my program, I am not always starting with an empty map and have to draw the walls every time. So if you spend some time drawing a map layout you like, you can just quickly save it. Just a quick and dirty way of doing that. Okay, so we've got our map, we've got our grid set up, we can find neighbors. How do we calculate how to get from one point to another? Well, as I said in the first video, we're going to talk about a few different pathfinding algorithms, but the first one that we're going to talk about is one that just visits every square in the map. Okay, and that is called the BreadthFirst Search algorithm. And let's look at how that algorithm works. So the BreadthFirst Search is also called BFS, and all it does is you have something called the frontier. The frontier is a group of tiles, an expanding ring of tiles coming out from wherever your start position is. And you just loop through over and over until that frontier is empty. And there's only 3 steps to this algorithm. First thing you do is you take the next location out of the frontier. You mark it as visited, so you keep track of which ones you visited so that you don't ever visit them again. And then you expand by taking that location and adding each of its neighbors to the frontier. And that's all there is to it. So let's look at an example of how that works. Okay, so here we have our simple 5x4 grid, and I've chosen this tile to be the starting position, marked it with a star. Now to begin with, the only tile that's in the frontier, and I'm going to mark all the frontier tiles with red, all the visited tiles with green. Right? We haven't visited anywhere yet, so there's no green tiles. You start out with your starting tile in the frontier, and that's it. So the algorithm says the first thing you do is you take the first tile in the frontier and you mark it visited, and then you add its neighbors to the frontier. So now the frontier has these 4 tiles in it. And we're done with one loop. Now we go back to the top. Is the frontier empty? No. So take the next one, mark it visited, and add its neighbors. And then we're going to continue doing that around and around, slowly adding more and more neighbors to the frontier until we get to a situation like this. See number 11 here. So when we mark that one visited, there's no neighbors. It has no neighbors to add to the frontier because these 2 are already in the frontier, and there's nothing over here because we're at the edge of the map. So it just gets marked visited, and we move on to number 12, which is going to do the same thing. 13. You can see we're slowly filling them all in until we have visited every single square. And that's it. That's the BreadthFirst Search. So let's look at an example of that running so you can see what it looks like in practice. So here's a big empty grid and this red tile. This is the starting tile, so it's the one in the frontier, only one in the frontier. And when I unpause this, you'll see it's just going to expand the ring just like we did in the demonstration until it has visited every tile. And what's great about this algorithm is it works just as well when you have walls. So if we look at another situation where we have all these walls, right, when this neighbor, when we look at its, or sorry, when we look at this tile's neighbors, it only has these three neighbors, right? Because this tile is not going to count. So this tile won't get added to the frontier. Same thing with all the walls. So when you run here, the ring just goes all the way around the walls until you visit everywhere. And that's why this algorithm is sometimes called the flood fill algorithm. If you've ever used a paint program and you use the paint bucket tool, you click somewhere in a shape and the paint fills in all the empty areas. That is exactly how that is implemented in a paint program, is using the BreadthFirst Search algorithm to do the flood fill. Okay, so let's talk about how we can implement this algorithm in code. So the first thing we're going to need is, let's look back at the algorithm for a second. So we're going to need a frontier, and we're going to need a list of visited tiles. Right, the list of visited tiles is just going to, so we keep track of which ones we have visited. And this frontier is where we're adding and removing the tiles as we look at them. Right? But we need to do them in order. The first one that we add to the frontier should be the first one we take out. And so we need what's called a queue. A queue is a data structure where when you add things at one end and you take them out the other. Right? So the first thing that gets added is the first thing that comes off. Just like when you stand in line at the store, you get in the back, you have to wait for the people ahead of you before you get to leave the line. And so we could use a list in Python to do this queue, right? We could have a list of items, and adding to the end is just using the append function of a list, add to the end. And when we want to remove, we would need to pop item number 0. Now the problem with this is, remember, lists are indexed, right? This is position 0, position 1, position 2. So if you remove the item at position 0, and you take it out, then everything moves, and this becomes position 0, this position 1, this position 2. Everything gets re-indexed, and that is slow. Lists are not really good at re-indexing quickly. That's not what they're for. So what if we tried the other way around? Right? What if we did it in the opposite direction? And we said that when we want to remove, we just use pop with no arguments, right? That means take it off the end. So pop will be fast. It'll just chop the 1 off the end. Item would be equal to 1, and 1 is removed out of the list. But then when we want to add, we need to insert the new item at the front of the list in position 0, which means all of these other ones have to be re-indexed again. And we have the same problem. So this is not going to be the optimal solution for this, because if you think about it, we're going to have a lot of squares to visit. We're going to have a lot of tiles to be added to this frontier, all the neighbors every time we look at a tile, and removed from the other end. And a list isn't going to be very efficient. The answer is to use something from the Python collections module. The collections module is part of the standard library that comes with Python and has lots of useful objects in there. The one we care about is called the deck. It's a double-ended queue. And this is a data structure that is set up to very efficiently, you can add items to either end, and you can remove items from either end. You cannot access items that are in the middle, right? You can't look at an index and say, what's the third item of the list? Because this isn't a list, this is a queue. And all you care about is the ends. But that's perfect for our situation. So the way we would use that is we can use append to put things on the end, and we can use pop left, which pops things off the left-hand side. You could totally go the other way around and do pop things off of this side and append left at this end. Doesn't matter, works exactly the same, and it's going to be very fast and efficient for all the tiles we'll be looping through. All right, let's start writing some code. So first thing we need to do is let's define our starting position. I'm just going to put it around the middle here. So that's going to be the starting tile. And then let's hide that. Let's define BreadthFirst Search. Okay. BreadthFirst Search works. You give it some sort of graph, and you give it a start position. Right, so we're just going to pass in those values, and that's all it needs. Okay, and so we're going to make the frontier be one of those double-ended queues, which we need to import. Okay, so we have the deck. We will put the start in it. That's the only thing in the frontier when you start. And then I'm also going to make a list of visited tiles, right? Which all it has in it at the beginning is the start, right? It's the only one we visited. And now we just need to start that loop, right? As long as len of frontier is greater than 0, right? So as long as there are things in there, we are going to loop through and do the steps of the algorithm, right? So the first thing is we'll pick the current tile that we're looking at is the next one in the frontier, right? So we pop the next one off of the queue, and that's our current. Okay. Now we need to look at the neighbors of current. We'll just call it the next tiles. So we take the graph and use our find neighbors function we wrote last step, and we find all the neighbors of the current tile. If the next tile is not visited, right, we haven't visited yet, then frontier, then we're going to add it to the frontier, and we're going to append it to the visited tiles. Okay? So we're sort of combining those two steps because it's just a little bit quicker. I wrote n twice. Okay? And then, so at the end of this, we will have visited all of the tiles. But how will we know? Well, I'm not going to write the code here to animate exploring because, obviously you don't want to do that when you're doing pathfinding in your game. So all we want to do is have it walk through and visit all the tiles. And so let's just, when we're at the end, print out the visited list and see if we've visited all of them just to test. Okay? So we run this by executing that. So here's our start. So if we just say BreadthFirst Search with our graph and start, and there we go. It lists a whole giant long list of tiles, right? But this isn't very useful because it doesn't tell us anything about how to get from tile to tile. This just visits every single tile and marks them visited, and that's it. And that's not good enough. So what we want is to be able to see, call this up again here. What we want is to be able to see how to get to the start. Our start's going to be over here. So if you're here, how do you get there? Or if you're over here, how do you get there? What's the path to that point from any other point? And we can do that pretty easily by going in here and changing. We don't care if, or we're not concerned about whether we visit it or not. We're concerned about when we visit a new tile, where we moved to it from. Okay. So I'm going to make a dictionary called path. The key will be a tile, and the value will be what tile we came from, right? So, for example, we can say the path to start is none, because, right, you're already on the start when you're on start, so you don't need a path to there. But anywhere else, when we look, if next is not in path, then we're going to path, the path for next equals, okay? And that's going to say, for example, that if you're on a tile here, then this tile should point back to this tile, right? That's the tile you stepped from. So an easier way to do this, instead of saying that 0, 1 is connected to 0, 0, is to actually put an arrow there. It's to actually have a direction. And the easiest way to do directions is with a direction vector, right? So if we said current minus next, that's going to be an arrow pointing from the next tile back to the current. Oops, I meant to say path here. Autocomplete. Right, and so we'll have a direction vector pointing the direction we want to go. Okay, and let's get rid of this print. Okay, now watch what happens when we run this. Okay, we get an error. Okay, and the error, this is hard to read, so I'll put it here. The error is unhashable type. Our problem is we're using a dictionary here, right? And the key of the dictionary is we want to use the tile we're on, and we're using vectors to represent the tile. Well, vectors, it turns out, cannot be the keys to a dictionary because they're not hashable. Kind of annoying. I thought about this for a little while. There's a couple different ways we could approach this, but so when you're doing a dictionary, the key can be any type of object, right? It can be a string, it could be a number, it could be a tuple, it can be a lot of different things, but it just happens to be, it can't be a vector. But it can be a pair of numbers like this, right? And so the easiest thing to do is let's just convert our vector into one of those. And I'm just going to write a quick little function that does that conversion. And it just returns the x and the y of the vector. And I'm putting an int here because when you, we are using integers for all of our tile locations, right? It's going to be 1, 1 or 5, 7. But when you use the Pygame vector2 function, it will send them back as real numbers. So you'll get 1.0 and 12.0. I'm just going to use the int function to strip away that decimal. Okay. So that means now that whenever we want to put something into this dictionary, we're just going to convert it to an integer. So we need to do that with this one and with this one. Okay. And that will take care of that error. Okay. So now we're getting values. So as the frontier creeps around and explores everywhere, each tile is going to have a vector pointing up, down, left, or right back to the tile it was on previously, the one it was the neighbor of, right? So like when this one was the current, these were neighbors. Whichever ones it added, they're going to point back to it. So we have little direction vectors for each of those. And just real quick, you can see that if we just print out the path, just so you can see what the output is. Each tile has a vector, and you see the vectors are all unit vectors pointing up, down, left, or right. Okay, and so let's visualize that. So what we're going to do is we're going to return that path. So whenever you run the function BreadthFirst Search, you're going to get back, you're going to get back the path. All right, so path equals that. So we have our path, we have all our vectors, we just need to draw them. And to draw them, I just have here, this code right here, which I've just pasted in, goes to the icons folder and gets an arrow, an image of an arrow pointing to the right. And then I just create a list of those arrows, 4 of them rotated in each of the 4 directions. So I have arrows pointing up, down, left, and right. Just 4 different images. You can import those, you can load those however you want it, but that's how I'm doing it. Just so that I have 4 different arrows and I can draw them here. And so what we want to do is we want to go through for each node and direction in that path dictionary. If there's a direction, because remember we're going to have none if we're on the starting tile, then we're going to get the X and Y out of the node, and then I want to find the center of the tile so I can center the arrow image. So that just means I need to take the X of the tile, multiply by tile size, and add tile size over 2. Okay, and I'm just going to do the exact same thing for Y. And then the image that we're going to use for this tile is the one that's pointing in the direction that we need. We're going to get the rectangle to match with the center at XY, and then we're going to blit it on the screen. All right, and if we run that, we should see a bunch of arrows. So here's our start tile. We'll probably need to draw something there too, but here's our start tile, and you can see from any point you can follow the path of arrows and you will get to the start point. Now the only other thing we need to do is if I add some walls, you see nothing changes because we're not updating. Right? Anytime we add or remove some walls, we need to rerun the search. So what I'm going to do here is if there's a click, whether we added or removed, we're just going to recalculate we're going to recalculate the BreadthFirst search. That way you can go in here and you can do things like closing off walls, and you can see how the arrows change, right, when you do that. And go all the way around. And if you block off an area, well, these are not neighbors of anybody anymore, so they're never going to get searched. So anytime you close off an area, it just won't get searched or included in the directions. So there you go. And that's our first version of pathfinding. Now, okay, let's just add one other thing, which is I want to add that if we click the right mouse button, then I just want to change the start to that position. Okay, and I want to recalculate when that happens too. So any kind of mouse button is going to make it recalculate. Button 1 will let us draw. Button 3 will draw walls. Button 3 will let us move the start. That way, you can also right-click and move the start position around and see how that changes, plus adding whatever walls you want. Right. Okay, so that is our BreadthFirst Search pathfinding algorithm. This is a really useful one for all sorts of different kinds of game applications. Like, for example, if you're making a tower defense, maybe your start is over here, so this is the destination. You're going to have the mobs all spawn over here, and then they're going to follow whatever path through to get around and get out of the level, and then you can predefine the walls, and the player can place their turrets and things wherever they want them to be. For something like our zombie game, this location will be the location of the player, and then how no matter where on the map a zombie is, it has a way of getting to the player, and it can roam around the maze and get to the player. And that's a lot more efficient than, if you have a lot of zombies, that's a lot more efficient than having each zombie calculate its own path, because then you have to do pathfinding 20 times. This way you do it once for the whole map, and anything on the grid can look at this vector field and head towards the player. Okay, so in the later videos we'll talk about some other different kinds of pathfinding, plus some other things you can do with this. We didn't really talk about diagonals yet. Diagonals are a separate issue, which can cause, you need to do things a little bit differently for, and we'll talk about that in a later video as well. I hope you enjoyed it, and I hope you have fun, and I will see you in the next video. Thanks.